Hi, my name is Alon Hovav. I'm a student of Professor Hierarchical, and today I will be presenting you our third research along with Adi Gottlieb and Sandeep Banerjee about novel properties of hierarchical probabilistic partitions and some of their algorithmic applications. So we present a framework which is based on a dynamic program and is efficient in solving problems with sparse solutions. Sparse in a manner which we will describe later, but it has many applications. And it uses probabilistic hierarchical partitions in a way which exploits properties which were unknown up until now. And it has applications in both clustering problems and in network design problems. Our main motivating problem, and the problem with which I will demonstrate most of the ideas, is minimum sum of radii. In the problem, we have a general metric space X with a metric function D, and we are given a parameter K. We try to cover the metric space using K balls such that the sum of the radii is minimal. Okay? Sometimes we assume that the doubling dimension of X is bounded by some constant D. Doubling dimension was already explained yesterday, so I will skip that for now. There are also many variants, like using MSR when allowing a certain number of outliers, MSD, in which you minimize the sum of diameters, and the clusters are not necessarily balls, and many other variants. But as I said, we will focus on MSR. So prior to this paper, in this research, exact MSR was solved in n to the 2 to the d for Euclidean metrics. And also it has a log n to log n log aspect ratio. Here is the aspect ratio of the space, the ratio between the largest distance and the smallest distance. And there were also approximations. There was a Q-pitas. For MSD, minimum sum of diameters, there was only a solution for the Euclidean plane. And it is known that exact MSR is NP-hard even in very simple metrics. We give these are interesting results, including metrics with bounded doubling dimension. Like even if the doubling dimension is small, and MSR is still hard. This is due to a paper by Gibson from a few years back. So, some background, yesterday Mohammed talked about Aurora's construction. Aurora presented pitas for a TSP, traveling salesperson, and many other problems in Euclidean metrics, which was based on a hierarchical partition with the thing Mohammed explained yesterday, with a randomized shift, and it's okay. Okay, now it's good. With a randomized shift and using this method of axis-aligned probabilistic partition, like yesterday we talked about constructing a tree from this partition, but there are also applications just to using this partition to solve traveling salesperson and other problems. And the problem with this approach is that it doesn't generalize to other metrics, non-Euclidean ones. And a few years back, Yair and Adi and also Robbie, which will be supposed to be speaking later today, shown a pitas for TSP in general metrics using another kind, a more general kind of probabilistic partitions. But the problem with this, as we can see here, was the doubly exponential dependence on D, which we avoid here in this result. So we begin with describing what are delta-bounded partitions. A delta-bounded partition of a space is a partition such that the diameter of each set is at most delta. Okay? And we consider hierarchies which are composed of delta-bounded partitions with factors of the delta decreasing. We use a factor of 2, like delta, half delta, quarter delta, down, such that the I-level partition respects the I-1 level partition. Here we have like the green cell, the encompassing cell, and the lower level blue partition is smaller, but it respects the higher one, and the purple one also splits again, and they all conform with each other. And so this is a partition and a hierarchical partition. And we consider a delta probabilistic partition as a distribution over delta bounded partitions. This is the standard way to refer to probabilistic partitions. And the main component, the main attribute of a delta bounded probabilistic partition is its padding parameter. The padding parameter is the probability, is a bound on the probability that a ball is cut by the partition. Okay? So if we have here a ball of radius r, and we have a delta bounded probabilistic partition with padding parameter tau, we expect the probability of the ball being cut to be bounded by r over delta multiplied by tau. The larger the ball, the higher the probability it is cut, and the larger delta, the smaller the probability. Okay? And we say that the metric space X has padding parameter tau if for every delta there is a delta bounded probabilistic partition with padding parameter tau. Okay? And up until now, it was all background about probabilistic partitions, and now it is time to define sparsity, which is unrelated to.
Can you back up? So just how should we be thinking about the padding parameter? Should we think of large padding parameter is good or bad?
Large padding parameters are bad.
Or not? What? Yeah. Large is bad.
The smaller the padding parameter is, the lower is the probability of cutting a ball. Like, okay. So, and intuitively, when you cut less balls, and then you can look at cells of the partitions more as parts of the space. You know, you're not splitting solution balls. You know, that's a solution. Mm-hmm. And also, I forgot to mention it, but we know that for doubling dimension spaces, tau is order of the dimension. Okay? And since the order of the doubling dimension is bounded by log n, we know that tau is always bounded by log n, order of log n. So about more questions? Okay. So more about the lambda sparsity. The definition is this: we are given a set of balls, okay, and we want to say that this set is sparse. And we say that the set of balls is lambda sparse if, when considering every other ball, Bxr, okay, and then considering all the balls from B contained in this ball, the sum of the radii is at most R multiplied by lambda. Okay? I will give an example shortly, and it will make it a little bit more clear. But you want to be able to say that the balls are not too densely packed. Okay? And I think that the best way to we also have a similar definition for non-ball clusters, which I will not get into now, but it exists. And I think that the best way to explain this is explain that MSR, that every solution to MSR is one sparse. Okay, and I will explain why. For each of the problems we consider in this paper, we have bounded lambda sparsity, which means that every solution can be sparsified without increasing the cost. We can obtain a second solution, which is lambda sparse, without any increase. For MSR, it's quite trivial, because if you consider B to be a set of solution balls to MSR, a cover, then and you have a violation. You have a ball, Bxr, which contains solution balls, such that the radii sums up to more of the radius of the encompassing ball. You can just throw all these balls away from your solution, replace them with the large ball, and now the cost of the solution wasn't increased. But and because during this process you reduce the number of balls, which is finite, at some point you end up with a one sparse solution. Okay? Mm-hmm. Does this simplify explains a little bit of the notion? I hope so, because it doesn't matter so much, but it's an important point. It's a technical point to some extent. Hmm? Yes. Mm-hmm.
So in the previous slide, I can see the probability linear on the radius. Oh, sorry, the one before that. Is there any reason why it should be linear on the radius?
I think that the constructions in which partitions with a specific padding parameter are given give this intuition, but this is like a very different topic than the topic of the of this presentation. But intuitively, as you make the ball larger, the probability that it is cut should be larger as well. I will not get into it any more than that. Okay?
Thank you.
So up until now, we have defined hierarchical partitions, and we defined the padding parameter and the sparsity. And now we need to define a few more properties of hierarchical partitions, which we utilize in our construction. The first one is cell formation. Okay? Now we have different cells in this hierarchy, and we say that I will say before the definition of cell formation, I will describe the standard way of creating hierarchies. We say that hierarchies are composed of partitions which conform with each other. So one standard way to create a hierarchy is given a hierarchy up to some level. We can partition each cell using a full partition of the space. I can take this blue and green cell, this one, and take a full partition which is delta I plus 1, bounded, of the whole space, and just partition this part using it, okay? And when we do that, we call the hierarchy intersection-based. We say that each cell in the final hierarchy can be presented as an intersection of cells from creating partitions, okay? And we say that a specific level creates a cell if it has importance in this intersection, okay? If we omit it from this intersection and it doesn't change the cell, then it doesn't form it. Or more intuitively, a cell is formed by a level if it has a border shared with this level. We can see here that this cell is composed of the purple level and is formed by the purple level and the blue level, but not by the green one, okay? If we change the green one, okay, we don't intersect the green cell, it doesn't change this one. But this cell is composed by all three levels presented in this sketch, okay? So this is cell formation. And we say that a hierarchy has LM level complexity if every I level cell is composed by at most L levels, which are at most, which are all in the range between I minus M and I. Like intuitively, each level is not formed by many levels, but by a small amount. And all these levels are only up the hierarchy up to some extent, okay? So this notion helps us to use a compact representation of a specific cell. We can present a cell using a small selection of like our building blocks, as we'll see later. Yes?
So, but you said it's like a hierarchical partition, so why can't you say that just the purple cell already forms the cell you specify there?
What do you mean? Which one? This one?
For example. Yeah.
This is formed by both the purple and the blue one.
If the purple is like a refined partition of the blue one, then you also can say that it's formed by only the purple one. I mean, why the blue is part of it? How the blue is different from the blue?
No, because when creating this cell, okay, I took this higher level cell, okay, and I partitioned it using an unrelated partition, which isn't a part of the hierarchy, okay? So I had this cell, which is already an intersection of such cells, and this cell is the intersection of the larger cell and a specific cell from the partition, which could have been like larger up to this place as well. So in order to present the cell itself, I need to maintain the previous levels, because otherwise I will get a different cell. Okay?
You should think about it like in Euclidean space, when you take balls or something, and only when you take the intersection of all the balls, you get the exact cell here.
Yeah.
So what's that P hat? there?
P hat, good question. P hat is the partition I use to partition a cell. Okay, if I use the partition, I use the partition, the purple partition, a specific purple partition to partition this cell. Okay, so this is a p hat. Okay,
It is
it's
external partition. Right?
Yeah, it's the external partition. So that was a level complexity. And another notion we have is of level complexity, of ball complexity. We say that a hierarchy have ball complexity B if for every I-level cell, there are at most B balls from the solution set. Okay, we consider these properties with regard to a specific set of balls. In our case, the optimal solution for MSR, such that it cuts at most B balls from this set with radius lower or equal delta I. Meaning, we are interested only in small balls which are cut. Okay, we know that, and if we go back to the definition of padding parameter, we know that we cut large balls with high probability. Okay, so we are not interested about them for now. We'll solve the problems with them later. But about small balls, we know that we cut them with lower probability. So we would like to bound the number of balls that each cell cuts, which are small with regard to this cell. Okay?
What's script B here? Script B.
Where?
Inside the set brackets.
Inside the set, here?
No, down below. In the definition of BI.
BI?
What's script
To the
B?
right, to the
The
right.
set of balls.
Okay,
B.
No.
B.
Yeah, set of balls. It has
this is the set of balls.
So there is some
Yeah.
Yes,
This
there is an
definition
external,
is with
as I said,
respect to
this definition is with respect to a specific set of balls, which will be the solution balls, okay? The optimal solution, the optimal lambda sparse solution in particular. So now we create a large family of hierarchical partitions in a probabilistic manner, and later we will show that there is a hierarchy in this family which has some specific properties which we would like to utilize. So we assume that our hierarchy will have n levels, okay? We can assume that. And we know that, and so we randomize, we sample these external partitions. We sample log n external partitions for each level. And now, given a hierarchy which was created up to some level, we can partition each cell using all possible permutations. We can all possible permutations of cells to external partitions, and this creates many, many more hierarchies. And this family is super polynomial, but we don't explicitly build it, so it's okay. We use the the level complexity in order to build only a small subset of it. Okay? Now, with this notion of this process, okay, we define another property, okay, which is validity. Okay, this is another property of the hierarchy. Since we know that the set of balls is lambda sparse, and since we have the padding parameter of the space, we actually have a good bound on the expected number of balls from the solution ball, which are cut by a specific partition. When we take a cell and we partition it and we consider only small balls, the expected number of cut balls is relatively small. Hence, we can say that a partition is valid with regard to a cell if, when partitioning this cell using this partition, we only cut up to a constant factor of balls from the expected value. Okay, so we will use this property, this validity, to show that given if we sample enough log n is enough, if we sample enough partitions, delta I partitions, some of them will be valid. Hence, we will cut small, with high probability, they will all be valid. There will be an all valid assignment. And we will have only a small number of balls cut. So the actual properties of the hierarchical partition which we will search for is as follows. With probability at least 1 minus 1 over n, okay, there is a hierarchy in the described family, this super polynomial family, which is both valid and has ball complexity lambda tau log lambda tau, when tau is the padding parameter and the lambda is the sparsity. Which means that for MSR in Euclidean d-dimensional spaces, this is actually d log d, which is quite small. And up until now, only bounds of log n were shown for similar properties. And the other property is that a hierarchy which was constructed using this process is with high probability has a square root of log n level complexity. It can't be formed by more than square root of log n levels, which are all up to log n levels from the current level of the hierarchy. Okay?
Sorry, I don't get the first item. So the set B, script B now of balls is part of the input, or
no,
it's for every set?
It's actually for every such set. Okay?
So for every set of lambda sparse, that is lambda sparse, you have
yeah. We use this set.
Collection of
we use this set only for the analysis. Okay? We know that there is such a set. Okay? And then we say, given such a set, with high probability we have such a hierarchy, but we don't require this set to construct the hierarchies which we construct. Okay? We iterate over possible hierarchies, okay?
Okay, so the quantifier is not like you said, right? I mean, it assumes that there is and exists, so with respect to some alleged lambda sparse set of balls, you have this probability, such a partition that will be okay.
Yes,
okay.
yes.
Okay.
Any other questions?
And the ball complexity is over all the levels together? So
Yes,
other level.
The ball complexity, each cell satisfies it with regard to its own diameter. Okay? So these are the properties. I will skip that because we have no time for it. But the dynamic program is as follows. Okay, we need a few notions in order to explain it. So we define a partition configuration with regard to a specific point x and a specific level I as all the possible ways which we could create the I-level cell creating x, or p in this slide. Okay? And since the level complexity is bound, we have a bound on the number of cluster configurations. And we can iterate over all possible cluster configurations, given that we have already sampled our partitions, which we later use. Now, given a partition configuration, we can consider cluster configurations. And a cluster configuration for a given partition is a set of balls cutting this partition. Okay? So how will our dynamic program work? It will start from below, the lowest levels, and for each cell, okay, it will enumerate over different possibilities of solution balls cutting this cell. And when going up the hierarchy, we will dynamically choose best covers. Okay, I will explain it in a little more detail shortly. So we have shown that we have a hierarchy H which has small ball complexity, and we also know that H has small large ball complexity. We have shown that each cell cuts at most lambda tau log lambda tau small solution balls. About large solution balls, this is a problem-specific parameter we call gamma. Okay, so we need to iterate over all possible choices of gamma plus lambda tau log lambda tau balls, which could cut the cluster. So in total, we have this amount of cluster configurations, where M is the descriptor of a cluster. Now, what is a descriptor of a cluster? In the case of a ball in a discrete space, the descriptor size is 2. We describe a ball using a center point and a point defining its radius. Okay, there is no need to use radii which are not directly up to some point. The problem is that for MSD, for more complicated types of clusters, the descriptor is larger, which makes this very large. But when m equals 2, it's quite nice. So, as I said, we start with the maximal level and ascend. And for each level and for each pair, we iterate over all partition configurations. And we iterate over all the cluster configurations. And we construct all possible solutions with different number of cut balls from 0 to k, because we don't know how many balls we would allocate later for this part of the solution. And then we iterate when doing this iteration. Okay, like considering an I-level cell, assuming we already computed the lower levels, the I+1 level or I+2. Okay. Given a partition configuration, it is easy to find the possible partition configurations of the lower level cells, because we just take an external partition and use it to get it. And it is also, due to the validity, easy to enumerate over cluster configurations. I will not get into why now because the time is short. And then we merge the inner solutions in like a small inner dynamic program in a short time, which depends only on k. So to sum it all up, the exact solution, and then I will say in 2 minutes something about approximate solutions. This framework solves discrete Euclidean MSR in n to the d log d, which this was the previous result. It solves non-discrete Euclidean MSR in d prime log d prime. And also it has this parameterization of tau log tau plus log of the aspect ratio instead of log n times log the aspect ratio. So I don't have much time for it, so I'll only say a few words about the approximation scheme. In order to solve the problem of large cluster descriptions in MSD, and also in order to save some time also in MSR, we decompose the space such that it has certain properties. One of these properties is that we have a bound on the interesting aspect ratio. I won't get into it now, but we augment the way in which we choose cluster configurations. Instead of iterating over all possible cluster configurations, we have approximations of possible radii, and for each approximate radii, we choose cluster configurations only from a given net. And for large candidate radii, we use a net proportional to the radii itself, which means we don't lose much in terms of the optimal solution. And for small candidate radii, we use for all of them the same net, which doesn't approximate directly too good, but in expectance it works because we have like a bounded number of levels. Okay, I think this line is the most interesting part of the paper. I will be happy to explain more about it later. But the general framework here for the approximation is to decompose the space using a process we will not describe. For each part, of the decomposition, for each component, take a net with respective with epsilon diameter of this component. Run the dynamic program on this component, and then merge all the solutions to a solution on the general metric space. So consequences, like this solves matrix MSR in this time, which is near linear. We have n only here. Okay. It also solves metric MSR with G outliers. In a manner which you can just replace naturally k with k plus g in the same times, which is nice. I don't think that more than a constant factor approximation was known for MSR with outliers up until now. It also solves metric MSD it's hard for me to say near linear times because of some of these factors, but like the dependence in n is linear. when up until now only approximations in the Euclidean plane were known. And it has also solutions to TSP, to many other sparse problems. And I think that this is it. Thank you very much.